Hello. Welcome to the Design and Analysis of Algorithms video seminar for our experiential learning topic, the Euclidean Shortest Path. The table of contents that will be covered in this presentation are introduction, methodology of two algorithms, time-space analysis of the following, the advantage and disadvantage of the algorithms, and the real-world applications. So coming to the problem statement, the Euclidean shortest path problem involves finding the shortest path between 2 points in a Euclidean space, where we are given intersections that we have to avoid, which are the intersections are a set of polyhedral obstacles placed within the spatial region. So given a set of polygons that are defined by the vertices and a start point which is the source and an end point which is the goal, the main objective is to determine the shortest path from start to end, that is source to goal, avoiding any polygons which are the intersections. This problem is also referred to as the shortest path through an obstacle field, or also called as the shortest path within a polygon with holes. The definition of the further elaboration of the problem statement is that this problem is a computational geometry challenge that involves determining the shortest path between 2 points in a Euclidean space while avoiding the intersections, which are a set of polyhedral obstacles placed within that space. So now coming to the connection and relation of this problem with visibility graphs. The given problem has a strong connection with visibility graphs. What are visibility graphs? They are basically graphs that connect nodes, points in the graph that have a clear line of sight to each other. In the context of the Euclidean shortest path, the solution is constrained to follow straight line segments, which means the answer will primarily lie on the edges of polygons formed by the obstacles. To find the optimal solution, one can determine the shortest path between the two endpoints by considering the visibility graph and selecting the most efficient path within it. Coming to the methodology, we have discussed two algorithms, the first one being a naive algorithm, which is more of a brute force solution in which each pair of nodes are checked for intersection at any obstacle edges. If no intersection is found, the edge between the nodes is considered in the visibility graph. Using this method, the complete visibility graph is obtained, and after this, the shortest path is determined using Dijkstra's shortest path algorithm. A more sophisticated and optimized algorithm is the visibility graph rotational sweep, which is an improvement over the brute force method, as it takes advantage of the concept of rotational plane sweep to efficiently construct the visibility graph. Coming to the detailed steps of the optimized solution, firstly we calculate the angle from the horizontal to all points in the VI. This step involves visiting every vertex once and performing trigonometric calculations. The time taken in this step is of the order of O of n. Next step, we sort the list of angles A in increasing order, which is done in O n log n time. Next, we calculate a list S of edges that intersect the horizontal. This step involves going through each polygon edge and checking whether or not it intersects with the horizontal line. In the worst case, this particular step takes O of n time complexity. The last step is to run a loop that runs through all the sorted angles. This particular loop performs a sweep through the vertices in the anticlockwise direction starting from the horizontal. Since this iterates to the sorted list, it again takes a linear time complexity O of n. This approach filters out and searches only those active edges which avoid the need to search for each and every edge, thereby providing better performance in comparison with the brute force algorithm. This is the pseudocode for the rotational sweep algorithm. Firstly, Vi is the set of obstacle vertices of the polyhedral objects and the query vertex V. We calculate the angle from horizontal to all points in the obstacle vertices. Then we sort the list of angles A in increasing order using an n log n sorting algorithm. Then we calculate a list S of edges that intersect that horizontal. In the fourth step, we iterate through the sorted angles list using a for loop, and there are three condition checks. If the query vertex is visible to Vi, we add that particular edge to visibility graph. If Vi has an edge E which is not present in S, then we insert that particular edge E into S, which is where S is the list of edges that intersect the horizontal. Now if Vi has an edge E in S, we remove that particular edge E from S. Now coming to the time and space analysis of the algorithms mentioned. The naive algorithm starts with picks one vertex and compares it with n minus 1 other vertices, resulting in a time complexity of O(n) square. Afterwards, each edge between the pairs need to be compared to n polygon edges, leading to a total O(n) cube number of comparisons. In addition to this, Dijkstra's shortest path algorithm is run, which requires an additional time complexity of O of E plus V log V, where E is the number of edges and V is the number of vertices in the visibility graph. Hence, to summarize the time complexity of the naive algorithm, the construction of the visibility graph takes O(n) cube time, and Dijkstra's shortest path algorithm takes O of E plus V log V amount of time. Coming to the time and space analysis of the visibility graph rotational sweep, we can observe that the sorting step takes O(n) log n time, and checking for intersecting edges takes O(n) time, leading to, by ignoring the shorter order terms and considering the higher power terms, it leads to a grand complexity of O(n) log n. This is a significant improvement compared to the O(n) cubic time complexity of the brute force approach, and this provides a more efficient, the rotational sweep algorithm provides a more efficient search step, focusing only on the active edges in S. Though the rotational sweep subroutine takes O(n) log n time, we need to run this particular function on each and every vertex, giving the overall time complexity as O(n) square log n, and then subsequently Dijkstra's algorithm can be used to find the shortest path. Coming to the pros and cons of the algorithm, the advantages are that the rotational sweep approach significantly improves computational efficiency compared to the naive method. It efficiently constructs visibility graphs for complex obstacle configurations. It is applicable and finds use cases in real-world scenarios with large number of vertices. Coming to the disadvantages of the algorithm is that it is not particularly suited for large data sets, which while more efficient than the naive approach, the rotational sweep method has a complexity of O(n) square log n, which might be problematic for extremely large data sets. Second disadvantage is that it is a tough and meticulous implementation. Achieving the desired outcome through the algorithm might demand a more precise approach, which alongside skillful management requires the handling of various special edge cases. Coming to the real world application of the algorithms, it's primarily used in robotics and path planning to help robots find the shortest and safest paths to reach their destinations while avoiding collisions with obstacles. It is also widely used in computer graphics and video game industry for determining which objects or parts of the scene are visible to the camera and only rendering those components, thereby reducing the number of unnecessary objects that need to be drawn and rendered. It is also heavily used in VR and AR technologies to reduce rendering overhead and result in smoother and more realistic experiences. It is also used in wireless sensor network deployment to optimize the placement of sensor nodes. It ensures that the sensors have clear lines of sight, thereby helping in efficient communication. It also helps in collision avoidance in autonomous and self-driving vehicles by safely navigating through traffic or complex road layouts. It also finds application in military and defense for terrain analysis, where strategic positions can be identified and potential obstacles can be located for military operations. With that, we come to the end of the presentation. Hope you had a good time. Thank you.